Hey there, chemistry. I want to talk to you today about the photoelectric effect and how it relates to the model of the atom. And so, before we kind of talk about how it relates to the model of the atom, I want to talk about what the photoelectric effect is and why it's such a big deal. So, this is actually how Einstein won one of his uh, Nobel Peace Prizes was for his breakthrough in explaining the photoelectric effect. And so here's the phenomena that couldn't be explained until Einstein's breakthrough. So this is the photoelectric effect. What we have here is a piece of metal. You can see that in my drop-down menu here, I can pick a bunch of different metals to test, and each metal is going to behave kind of differently. So what the photoelectric effect is when light shines on the piece of metal, that light can actually knock off electrons. So these little blue spheres here are all electrons. The light is shining on the metal, it's knocking the electrons off, and the electrons are flying from one charged plate to another charged plate. And then they go through a wire. You can see there's a current here, and then the whole process starts all over again. So that's all the photoelectric effect is. It's just light that knocks electrons off of metal. Now, here's why it's such a big deal. If we change the wavelength of light, notice that I have this control up here, and I can choose a wavelength of light to shine on the metal. And not every wavelength will knock off an electron. And that was very strange. And here's why it's so strange. Let's pause this and let me tell you, if light was a wave, here's how it should behave. We have talked about the properties of waves before, and we have seen that when one wave meets another wave and their crests line up, we see that the altitude or the amplitude of those two waves will actually add up together, and what you'll get is a bigger wave, and that's called constructive interference. And so waves can actually build upon each other and become bigger and bigger and bigger waves with more and more and more energy. And we've seen this with waves at the beach. If one wave is rolling in and a second wave catches it, those two waves can actually build together and carry a lot of energy with them and crash as one big wave on the beach. That should happen with all waves, light waves, sound waves, water waves. That should happen with all types of waves. And so what should happen is my little low energy wave here that is striking a piece of metal. If that's not enough energy to knock off an electron, what should happen is that other waves together should be able to combine and build into a big wave that will knock off an electron. Or if one wave doesn't do it, we should be able to build like 10 waves, and all 10 waves together should be able to knock off an electron. But as you can see in this simulation of the photoelectric effect, that's not the case at all. This light doesn't have enough energy. These waves are not building on one another in order to knock off the electron. So we don't need more waves. That's what intensity would be. We can play with this slider up here and we can see that, okay, at zero intensity, I have no waves. And then I'm just building more and more and more and more waves. Well, we can move that intensity slider all the way up to 100, and it doesn't knock off an electron. The only thing that does knock off an electron is moving the slider that changes the wavelength. So we don't need more waves to knock off an electron. We need a different wave to knock off an electron. And you'll see once I pass this threshold frequency of wavelength, above that frequency or above that wavelength, all the wavelengths will knock off an electron. I can go all the way up into the ultraviolet radiation range here, and it's going to knock off electrons, right? So I don't need more waves. I need a different wave. And the wave model couldn't explain this. Light acting like a wave couldn't explain this. And so what Einstein said was, well, what if light is not only a wave? What if light acts like a wave sometimes, but it also acts like a particle sometimes? What if this energy that's contained in light is actually a little bundle of light? And so we don't need more waves. We need a bigger bundle of light. And once our bundle gets to be big enough, then it can actually knock off an electron. And that is where the equation E equals H nu came into play. So here's our frequency. If we have a low frequency, we're going to come out with a small energy. If we change the frequency of light to a higher frequency, we're going to have a high frequency of light, and we're going to have a large energy. So again, we don't need more waves. We need a bigger packet of light, a bigger bundle of light. And Einstein called those bundles photons. And this is the energy of one photon. And so he did a lot of experiments. He wrote calculations and equations to match those experiments, and those equations could actually predict what would happen with different light and different metal. And he was eventually awarded the Nobel Peace Prize for his work with the photoelectric effect. Now, why is that so significant to us? Why do we care that light has this phenomenal ability to act like a wave and also a particle? Well, we care about it because we're studying the atom, and the atom is made out of particles. And some of these particles and their behavior couldn't be explained by chemists. And the Bohr model is a good example of that. If we look at the Bohr model, remember, okay, if we're looking at lithium, for example, it has a nuclear charge of 3+, has 2 electrons in the first ring, and it has 1 electron in the second ring. Remember, Bohr took the model of hydrogen, and he built equations that lined up with the line spectrum for hydrogen, right? And he wrote all these equations that could predict the behavior of hydrogen's atom and could bridge that gap between the model of the atom and the line spectrum. So Bohr did this great work with the hydrogen atom. But the problem with Bohr's model is it only worked for hydrogen. It didn't work for anything else. It didn't work for helium, which has 2 electrons. It doesn't work for lithium, which has 3 electrons. It doesn't work for any of the other elements. And so Bohr made this beautiful, amazing model for hydrogen that didn't work for any other atom that has more than 1 electron. And so they're having a hard time. What the chemists were having a hard time with was explaining the behavior of an electron as it acts as a particle. And after this breakthrough that Einstein had with light and the dual nature of light, the dual nature being both a particle and a wave, well, some theoretical chemists took that information and they said, well, what if everything has a dual nature, not just light? What if electrons have a dual nature? And so that would mean that electrons could behave like a wave sometimes. And one of the things that electrons do is they interfere with each other. Remember, when we looked at wave interference and we looked at the patterns that emerge when waves interfere with each other. We looked at some water examples. We looked at some light examples. We looked at the Acura commercial. We looked at the salt on a speaker, and we saw that the more waves you get interfering, the more complicated your patterns get. And so this was the breakthrough moment for chemistry, is considering perhaps electrons also have a dual nature. Perhaps electrons act like a particle sometimes. They have mass, they have a volume, they are matter, okay? But perhaps they also act like a wave at some point in time. Perhaps they interfere with each other, and this is why Bohr's model only worked for a one electron system. Waves that interfere create patterns. Well, if electrons interfere also, they would create patterns, and those patterns wouldn't be the same patterns that would occur in a one electron system. And so chemists like Einstein and Bohr and Max Planck and Heisenberg, they all started to look at interference patterns that electrons could make with each other. And here is what they found. This is an example of electrons influencing each other. It's as if electrons, because they repel one another, they're pushing each other into certain spaces or pushing each other out of certain spaces. This is what we call a probability map. And a probability map is made if you take a snapshot of an electron every second and you overlay all of those snapshots, you begin to see a shape in which the electrons spend time, and you also start to see areas where the electrons do not spend time. And eventually you can draw an outline around 90% of the probability of where you would find the electron, and you get this shape out, and those shapes start to look a lot like interference patterns of waves. You can see a couple shapes up here. They're labeled 2s, 2p, and then here there's a whole bunch of shapes overlaid with each other. Here are other interference patterns that electrons can make when they interfere with each other. And so we start to see that the place where electrons spend time is a result of their interference with each other. And we start to see that the space where electrons spend time, okay, let me write this down. Interference patterns is three-dimensional. The place where electrons spend their time is going to be a three-dimensional space. It's not going to be an orbit as Bohr described it. Bohr described it as a little track, like a racetrack, where electrons spend their time. And we can see from these interference patterns that that is not the case. That is not the case of where electrons spend the time. They spend their time in three-dimensional spaces. And these three-dimensional spaces, they then named orbitals. Orbitals. Okay, so we're not going to say that electrons exist in orbits anymore. We're going to say that electrons exist in orbitals, which are a three-dimensional space caused by interference patterns of electrons with each other. And we can map them out as an area of probability where we are likely to find the electron inside these shapes, and we are unlikely to find the electron outside of these shapes. And that is what the quantum mechanical model was born from. And this is our currently accepted model of the atom, the quantum mechanical model, which describes a nucleus that contains protons and neutrons, and it describes structure around the nucleus for where the electron tends to spend its time. So what we need to go through next are the descriptions of these orbitals and attach those to certain energy levels. Okay, so to describe the orbitals that the electrons spend their time in inside the atomic model, we need something like an address. So if we look at the address of the school, it's something like, I don't know, 1500 Northwest 17th Street, McMinnville, Oregon, right? Okay, so we have a couple different pieces of our address that tell us exactly where something is located. We have a state, which is a large area, right? It eliminates the whole rest of the earth except for one state. And then within that state, we zero in to a city. And within that city, we zero into one street. And then within that street, we zero in on one building. So it's like a code. It's like a code that tells us where something is located. Well, for the electrons, we have a similar code. We have a code, and it's made up of N, L, M sub L, and M sub S. And each part of this code, it starts very general, and it brings us closer and closer and closer and closer to the electron's location. And when you have all four pieces, it actually tells you where one electron is located around the atom. So that code is what we need to break down next. So let me tell you what all these pieces represent. Okay, N is going to be the energy level. That's like our state. It zeroes us into one really large area. Now, energy levels can be whole numbers. So we could have the first energy level, the second energy level, the third energy level, and so on and so forth. But you're never going to have a decimal. Now, within each energy level, we have subshells, kind of like cities. And this subshell we call L. And these subshells tell us if the energy level zeroes us into one particular size, the subshells tell us what specific shapes live inside that. Okay, and the shapes, there are specific shapes that can live inside each energy level. So the shapes can be anything from N to N minus 1. So for example, if we're talking about energy level 1, we're going to have shapes from 1 to 1 minus 1, which is 0. Oh, okay, so we really only have, actually, this is not from N, sorry. This is going to be from 0 to N minus 1. So we really only have one shape that can exist inside the first energy level, and that is the S shape, which is a sphere. If we look at the second energy level, however, we can have all the shapes from 0 to 2 minus 1, which is 1. So we can have two shapes inside that second energy level. We can have the 0 shape, which is S. We can have the 1 shape, which is P. And a P is a dumbbell. And so that's why on the periodic table, on that very first row with hydrogen and helium, where they each only have one ring, right? That's the first energy level. And there's only one shape inside that first energy level. And that shape is a sphere. But when you get to the second energy level, that second row on the periodic table, you can have two shapes. You can have a sphere and you can have a dumbbell. Okay, now there's actually 4 shapes. So let me tell you what all of those shapes are. There's the first energy level can have an S shape. The second energy level can have an S and a P. And the third energy level can have an S, a P, and a D. Okay, D's kind of look like, if S is sphere and P is dumbbell, D's kind of look like clovers. And then there's a fourth shape, there's an F, and we see that on the fourth energy level. So 4S, 4P, 4D, 4F. Fs are crazy. They're all over the place. They are, there's no one consistent shape. And so I'll show you a couple examples of those, but you don't have to know a specific shape for the F orbital. Okay, so we have our energy level, which is our size. We have our L, our subshell, which is our shape. Now M sub L is going to be our orientation. So each of these shapes can be oriented in a specific way. So orientation is going to be from negative L to positive L. And the number of values you get here just tells you how many different orientations you have. So for example, for 0, you can go from negative 0 to positive 0. There's really only one orientation for the sphere, which makes sense. If we take a ball and we rotate it, it really doesn't look any different at all. For the dumbbell, though, which is shape number 1, we can have -1, 0, and +1. So we see 3 different orientations for the P dumbbell. It can be oriented on the x-axis, which is 1 orientation, the y-axis, which is 2, or the z-axis, which is the 3rd orientation. And so the L or the P shape can have 3 different orientations. The D shape can actually have 5 orientations, and the F shape can have 7 orientations. Okay, so M sub L is orientation, and that gets us a little bit closer to our electron's location. So this would be like the street. And then we have M sub S, which is the spin. And the spin is the least complicated of all the shapes. The spin can either be spinning up, which we call 1/2, or the spin can be spinning down, which is -1/2. And so this would be like the house. If you describe all of these, energy level, shape, orientation, and spin, you're going to describe one specific electron in the specific atom that you're looking at. So these are our different shapes, and we're going to do some practice with this next class. So stay tuned. Let me know if you have any questions, and I'll see you in class.